Okay, hydroxide could add to carbonyl. We can get this. Is that reasonable? Certainly it's reasonable. Any nucleophile could add to carbonyl. What could happen next though? This could pick up an H from water, right? I'm not going to show it quick, but if that picked up an H, what would you get here? What do you call that? Make the hydrate. Okay, certainly you can make the hydrate. But then we know, are hydrates stable? No. I mean, the hydrate is like, it's like this. And really, it's like this. So while this is possible, this is just not a favored pathway. What else could happen? I mean, you could maybe put H here, and then electrons would come in and kick off something. But if it did, and you remade carbonyl, what would that give? That wouldn't give anything good. You could do this, and what does that give? Right. What I'm trying to say here is that sometimes students say, well, why doesn't hydroxide add to carbonyl? Well, it does, but it doesn't give anything new. You can show hydrate, but hydrate we know is not the favored form. It's a very minor form, except for very special cases. Okay? So yes, it can do that. What else can it do? It can also act as a base, and we can remove H's here or here. Now, which is more acidic? Well, they're both. They're both similar acidity. You can make an argument for one or the other. Let's see. This is going to be making a ring. What size rings are best?
6.
5 or 6?
6.
5 or 6 are both good. If we made anion here, which is possible, what could it attack? Okay. Attacking this is not a reaction. That's actually resonance. Okay. But it could attack here. If it did, what size ring would that be? 1, 2. That'd be a 4-membered ring. Okay. Well, what if we made anion over here? What could it attack? If we attack here, what would that give? What size ring? It's going to give a 6-membered ring. If we draw that out, it is a 6-membered ring. Well, let's see where we are here now. I'm going to call this carbonyl A, and that B. So I'm just going to say, hey, here's carbonyl A, and then the carbon next door attack carbonyl. Okay. 6-membered ring. Carbon next door attack carbonyl. So we made this bond. That's the carbon next door. This used to be carbonyl. So what is all on this carbon then, here? The thing that links it back, but what else is on that carbon? O minus. And what else? A methyl. There's the methyl, and it became O minus when the electrons moved on to oxygen. So you have to sort of put it together about, okay, what connected to what. And guess what? If you never sit down and think about it, you're not going to be able to do it. But does everybody agree that if that carbon attacked that, we would get that? Okay? Now, ultimately, in our mechanism, I'm not going to take time to go all the way through, but if you go back, this picks up an H. I reckon I'll just go right through, but I'm not going to show full mechanism. Boom. Doesn't that pick up an H? I can't draw bonds connected. But I will tell you that's a 6-membered ring. This is sort of the aldol product. We got the alcohol, the all. But what happens here? Doesn't this lose water? And when we lose water, we end up putting the double bond where? Right here? Right here?
Better in between other carbonyl.
It's going to be the conjugated double bond. Because we're essentially, the base is going to make anion here, and then it comes in and it kicks off that hydroxide. You get the double bond there, it's going to be conjugated. So what's the product going to look like? Be double bond there, And what's coming off this carbon? Yeah. Okay? So you got to know your mechanism and just rationalize your way through it, and here's your product. An alpha beta unsaturated carbonyl compound. But we made a ring. We made a 6-membered ring by an intramolecular aldol condensation reaction.
How is that anion made to kick off the hydroxyl?
Well, you got base. I mean, this takes H from water, and you create hydroxide. Then hydroxide comes back and takes an H. Because aren't these acidic H's because they're next to the carbonyl? Yeah. Okay. We're not going to take an H off there and make double bond there. Double bond comes from making your enolate carbon and then expelling that leaving group in a fast step. And the double bond. So you have to know your mechanism, rationalize your way through it to see the products with it from here. If that had attacked over there, it had been a 4-membered ring. While you could show that, actually, why don't we do this? Why don't you show the 4-membered ring that would form from the aldol? You could theoretically show the 4-membered ring. Can you show the 4-membered ring? Okay? We have this 4-membered ring because the carbon next to the carbonyl may bond to carbonyl. That used to be carbonyl, electrons up, then pick up an H. Then you get anion over here, and then you expel the leaving group. That's how you put your double bond in.
There's a methyl methyl.
Yeah, see there's a methyl there too. Very good. Yes. That was the carbonyl carbon. Yeah. Alpha beta unsaturated. Okay? All this is in equilibrium. It can come this way. Which way is it going to migrate towards? 6-membered ring. It's going to be more thermodynamically favorable. Okay? Now, of course, if you made anion over here, you would get the same 4-membered ring. If you made anion here, you'd get the same 6-membered ring. What size ring are we going to make here? 7 or what? 7 or 5. Which is favorite? 7 or 5? 5. Okay, this will be a 5-membered ring. What would it look like? Let me see if I can just draw it from scratch here. The favorite is going to be this attacking here. 5-membered ring. The carbon attacks there. We're going to get an OH. Here's the carbon. That's actually going to be coming off. Doesn't that come from the carbon to the right of that carbonyl attacking that carbonyl? Hold on, there's a methyl there, right? Yeah?
Yeah.
And then when that loses water, then we're going to get what? Double bond there. Here. The 5-membered ring is going to be favored over the possible 7-membered ring. We should be able to show the 7-membered ring though. This is an aldol condensation. This is intramolecular. We had one of these on the quizzes, on the quiz. How would you make these? Which one would you like to do? Varsha? Third one? Okay, can you break the third one apart into two reacting molecules? We have an alkene. One of the carbons could be an enolate, originally an enolate carbon. Which one could be an enolate carbon, top or bottom? Top. So it's next to the carbonyl. I could break this down into, boom, that plus what? What do you want the bottom carbon to originally be? Aldehyde. Aldehyde. Yes, these two would react to give that. This would be an enolate carbon. Not only is it activated by the ketone, it's also activated by the nitrile. This is a doubly activated methylene. Remember those? Okay. Good acidity. So we get anion formed here, and then this attacks. You get your aldol with the OH, and then it eliminates the bond in. The OH in here is eventually eliminated off. These all are enolate carbon, carbonyl, enolate carbon, carbonyl. Ah, what do you see about this guy? That's a symmetrical aldol. This is not. This is a mixed aldol. That's a mixed aldol. This is intramolecular because you can break this apart into what? One, two, three, four. 1, 2, 3, 4. Treat this with base, anion formed here, and then it attacks and you make 1, 2, 3, 4, 5, 6-membered ring. This oxygen eventually lost as water. That's how you get your double bond here. Okay. Now there's actually another 6-membered ring you could get because 1, 2, 3, 4, 5, 6. That could attack that. That'd also be a 6-membered ring. At that point, we have to consider it. Do you have any selectivity for the two 6-membered rings? Let's look at the other handout. Aldehyde ketone warm up. This page here is a synthesis of Vioxx. All but one of these reactions we've now covered. Vioxx used to be $1 million, or actually $1 billion selling drug before it got pulled due to heart side effects. Anti-inflammatory compound here. Okay, got 20 carbons, a sulfur, some oxygens. Okay, see the $1 billion here? Okay. This compound is made by first doing a Friedel-Crafts reaction, put the ketone on. Sulfur's been oxidized. We never covered any chemistry like that, but sulfur can be oxidized at oxygen. What is this? Alpha bromination. They're doing it under acidic conditions, so they're able to put just one bromine on, as opposed to exhaustive. Then they come in here with this nucleophile and do an SN2 and kick off the bromine. So that's how they get that there. Used to be a bromine there, but now they have the nucleophile there. Then the last reaction is a intramolecular aldol reaction. They use trifluamine. Trifluamine is strong enough to do an aldol. Aldol is really an equilibrium reaction, and it's driven towards the product. Can you visualize what enolate carbon is attacking what carbonyl? Well, here's your ring that's formed. Here's your double bond. Of the two carbons, which was your enolate, top or bottom? Top. Because it's next to carbonyl. The bottom originally was what? Okay? So if you break this apart and call that A and B, where's A over here? Isn't that A? Yeah, you get anion formed here. And what does it attack? It attacks this over here, and so that's how you get this ring made here. This phenol probably enhances the acidity of these CHs a little bit because of resonance here. But you treat this with a little trifluamine and boom, it'll lose water. And you get this, and there you go, there's $1 billion. Okay, let's look at the Michael reaction. Let's try to get this to the main highlights here. This is the introduction. You have a nucleophile. If you have these alpha-beta unsaturated carbonyls, there's two different ways nucleophiles can add. You can add to carbonyl. Okay? Electrons up. And then from there, you can pick up an H, you can do other chemistry. But we've been doing that for 6 weeks. That's called direct addition to carbonyl. It's also called 1,2 addition. Why is it called 1,2? Because if you label that 1, where do the electrons end up after the nucleophile comes in? They end up on the oxygen. So it's like 1,2. You attack here, the electrons end up there. The 1,2 relationship. There's nothing new there. What's new is these guys, the nucleophile can also add at the beta carbon. And electrons move here. Now we give this, right? Now typically you don't add to alkenes like this. Typically in organic 1, alkenes are always nucleophilic. The alkene attacks something. Here the alkene's electrophilic. The nucleophile is attacking it. That's rare. Except when you have this situation, alpha beta, and then you have it's conjugated with the carbonyl. Because the resulting anion, does the resulting anion have any stability? Yes. Yeah, it's enolated. Which we know is stable enough to be formed. So that's why this can happen. Then you pick up a proton source, you can just put a proton on. You see it now has 2 H's, and you get a neutral product. Now look at your quiz today. Isn't that what we did on the third reaction? What did we do on the third reaction? Here we go. These add here, electrons here, right? What does that give? Gives this. The nitrogen has 2 H's. We didn't magically just lose an H. Call a Michael addition. There's other names, they'll say. What's going to happen from here? What looks like should happen here? Yeah, this wants to get rid of an H, that wants an H. H plus transfer will give you your product. There's an extra H there now. Now this is called a 1,4 addition because if you count that as 1 where the nucleophile added, where do the electrons end up? Well, it looks like they're there, but are they really? No, because we know that the enolate is really has resonance that looks like okay, we don't always draw this, but we drew it at the very beginning. Which is your major resonance structure? Okay? We need a review. Go back about 2 weeks ago when we first introduced enolate. There's your major resonance structure. So it looks more like this. So if the nucleophile added here, where are the electrons mostly now? Yeah. That's why it's called 1,4 addition. It's also known as Michael addition. It's also known as conjugate addition, because the double bond is conjugated with the ketone, which allows this to happen. So it has multiple names. Michael addition is also called Michael reaction. Okay. Now, there's some things here we just don't have time to look at. You can read this. I think to summarize this is, well, the question we're going to ask is, if you got a compound like this, when do you do direct and when do you do Michael? Depends on the nucleophile. Some nucleophiles prefer to add direct, some nucleophiles prefer to add Michael. Well, the one on the quiz was an amine, and amines prefer to add Michael. Why is the other the minor product? Is that what you asked? Yes. Yeah, because you could directly show a 1,2 as a minor product. The major product for amines is Michael addition. Why? Well, it's kind of summed up here. And instead of reading it to you, let me sort of tell you. If the addition to the carbonyl is reversible, it's going to come back off the carbonyl and end up going Michael addition. Because addition to the carbonyl, direct addition is actually kinetic product. That means addition to the carbonyl is fastest. And so the amine actually does add to the carbonyl first, probably. And that would give an imine. But are imines reversible? Yes. Yes. If it's reversible, it's going to come back off and it's going to add Michael. Because the Michael product is actually your thermodynamic, more stable product. So if it can reverse, you're going to get Michael. But if it can't reverse, it's going to add the carbonyl first and it's going to be stuck. And so you can't get Michael because it's stuck on the first addition. What type of nucleophile is stuck and cannot leave? Like a Grignard. So your Grignard, like a methyl anion, will add to carbonyl because that's fastest, and then game over. It can't then leave and come around and do Michael addition. So that's what this is saying. In the end, things like Grignards and hydrides add to carbonyl directly, and that's the product you get. So show the product here. This is a Grignard, then H plus work done. That's going to be your product. Your methyl anion is going to add here, because that's fastest. That's what it means, the kinetic product. Electrons up. We're going to get methyl added. There's an extra methyl added, O minus. And where does the H come from? Work up. Okay? So this is an example of Grignard doing a 1,2 product. Well, guess what? Remember these guys, cuprates? Cuprates actually do a 1,4. You might say, hey, isn't this also a minus source? And if it has some carbonyl, why is that going to reverse? It's because with cuprates have copper, and it actually makes the Michael addition be the kinetic product. We don't have time to go into why. It's the magic of copper. You just sort of have to know that cuprates add Michael. So now that you know that, show the Michael addition product. So your nucleophile just adds here, electrons here. And this is here's your enolate that's formed. What's the H plus workup for? This just picks up an H, and there's your product. There's your H there.
Would the electrons be more stable next to the ring, the benzene ring? If there's also
How would you get electrons here?
If you added the, actually it's not 1,4, never mind.
You want to add here and put minus here?
Yeah.
Well, you could argue for some stability, but it's much more stable to be,
Okay.
because this allows you to put resonance on oxygen.
Okay.
So at the bottom, you can see how you get two different products. Grignard adds 1,2, cuprate adds 1,4. Let's try to finish this up. Seems like we're missed a day. Here's some examples of amines adding conjugate addition. This is just like the quiz, right? Oxygen also adds conjugate addition. So your ethoxide comes in, and then you pick up an H from like solvent. Because the enolate will take an H from ethanol because of the pKa difference. Synthesis there you can look at, but here's the anti-cancer drug that's on the cover of your workbook. And there was a question of how this could react with a nucleophile. This enzyme, I think, has an SH nucleophile. Where do you think this reacts at? It actually does a Michael addition right there. These alpha beta unsaturated carbonyl cover, the double bond is very electrophilic. And the enzyme reacts right there, and the enzyme becomes covalently modified, and it leads to killing the cancer cells. Okay. I'll look back at where we, if the semester was shorter. I know usually we end on a Monday, on Wednesday. I don't know if the semester was shorter or not. We seem to be missing a day. Okay, test is on Friday. It has to be Friday because we turn on Monday. What do we got? We have, we began with simple additions, hydrates. You do need to know the functional group names, hydrates, cyanohydrins. Then we got into amines, acetals, variety of reactions with amines like Wolff-Kishner reduction, hydrosomes, etc. Then we moved on to like the Wittig reaction, Then we move to this handout, alpha halogenation, enols, enolates, tautomers. You have everything there. Same format, multiple choice, predict the product, mechanisms. Will be a comprehensive spec problem like I mentioned. We also have nomenclature, which is the second part of the video that I put up a while back. Aldehyde ketone nomenclature. Other questions about the test? You've got to be able to rationalize mechanistically, like when we're doing those rings today. You've got to be able to think how this is being put together. If you think you're just going to sit down and draw out the product without thinking mechanistically, you'll have a tough time. Of course, if you have any questions, stop by. Anything we're missing? Could be give reagents. Yeah. Don't have enough time. There's a handout that talks about the chemistry of superglue. It's basically a microreaction where it polymerizes. Because when you do the nucleophile and you get this anion, it can pick up an H, but see, it can also add again to another double bond. Superglue. Also, the chemistry of Tylenol, while it's toxic. Why is Tylenol toxic? Because Tylenol is converted to a alpha-beta unsaturated carbonyl compound in the body. And then your proteins in your liver start reacting with that by microaddition. If you take too much Tylenol, you're going to get a lot of that going on and kill your liver. So that handout front and back is pretty relevant. Okay guys, have any questions, let me know. See you in lab this week. Check it out. You're turning in your lab from last week.